Hello and welcome to Chemistry 10. Okay, so I've been doing some interesting things this time around. Um, yeah, it's kind of been interesting what I've been doing because I was thinking I don't want to move on to orbitals just yet, but I probably actually am going to move on to orbitals. But at the same time, one of the useful things I actually did was actually made a graph of the successive ionization energies. And these energies, there's one more thing actually I want to say. Um, if you've got like a if you've got like multiple like if you've got like multiple, I don't want to say one plus, I guess it would just be one plus one. Like I think it is just this. It must be one. So one atom of hydrogen that looks like octo or something, but it does say atom. um, and another atom of hydrogen, something I didn't really allude to before. I just want to mention it now. Is one molecule of hydrogen. And at the moment with chemistry, we don't want to be thinking about, compounds and stuff like that. Like obviously, if we have two atoms of hydrogen gas and an atom of oxygen gas, then we get a molecule of water. Water is kind of interesting. But yeah, so I've been looking at a lot of different stuff, but at the same time, I've still got a fairly good idea what I want to do here. Yeah, and just one more thing: the water, which is obviously H2O. Um, um, this is the compound empirical formula. So yeah, we're going over my table, but I've shown it in the last few episodes. It doesn't really matter much. And then I'm going to still try not to go over it. Compound empirical. Let me just try to get a bit more. Where's my mouse going? Formula. Well, it's going to have to do for now. So anyway, so as we spoke about before, I said I wanted to do a graph, and yeah, and I've done this graph here. Yeah, I wanted to have the little balls on the graph, but instead I've just got the balls and then just a line graph. I think with the balls, call it scatter graph. I need to check my graph names as well. But yeah, the advantage of this is that if we just take like this line here, and I'm not, I could try drawing a straight line, but it's perhaps not the best idea. And this, like I say, like for instance, I could have just drawn this graph out, but I don't think it would have ended too well. So I did decide to actually do that. But now, of course, with a graph, we do need to label the axes, and that's something which I don't mind being a little bit messy with. So I'll just put the axes here. So this is, yeah, we'll be covering this in maths pretty soon, but not yet. Still on exponents. But basically, just it's the only real thing is just to say the numbers are too big to put the actual numbers in. It'd just be a ridiculous graph. Yeah, I mean it's like you wouldn't put something with like a number with like 100 digits in a graph, or what have you. Oh no! Oh well. Yeah. And then this axis is going to be the number of electrons removed. So I think we could perhaps put cardinality symbol. So yeah, these are finite amounts of electrons removed. So you can see here that yeah, so it's about 2 point, yeah, and I said it pretty. So yeah, so these are obviously 0.1 increments here, and you can see on the line graph underneath. It's not actually such a bad idea to do that. because sometimes you can tell stuff from just the points, and you can tell different things from the line graph. Of course, I did actually, but yeah. So you can see anyway. The whole point of this was to show that look, at this area here and this area here, if we look at the number of electrons removed, well, we can actually just, fortunately, actually, it's kind of convenient, isn't it? It's right underneath it. See, there's the 10, there's the 2, 8, the 8 in the outer shell there. We can see this big increase in energy, both, and this is for sodium. Yeah. So it does actually appear that the energy in the, just looking at the graph, yeah. Yeah, you can see the energy is. That's interesting, isn't it? Because if you look to the table, it doesn't actually look like that. If we look at what is going on at 10 here, it just looks like it's gone boom from 9 to 10. And again, boom from at 2 when we go up to. Yeah, this one of the problems was I didn't actually want it. This is not actually a point. This was merely just to actually graph the thing. So yeah, this is not actually a point, but I needed to do it for the graph because obviously I didn't want the graph just to go like that. But yeah, that's a small site, and of course, you know, as time goes by, all the graphs will look better, and they'll get, you know, nicer colours and all this stuff. But yeah, so yes, that's the kind of, yeah. So that's pretty much yeah. Okay, so let's just write this down. Just need to try and get a little. Yeah, I normally just. Let's try and get this a bit better. Sometimes I get really flawless writing, sometimes not so much. Let's just try and write a little bit. Let's try and get this into. Let's try and get a little bit. Yeah, I think I just need to press a little bit harder with the pen. Some of those points. I can't remember. There was something in the documentation for that. All right. So that's basically yeah. So there's the graph of the ionization energies. But the but yeah. So so what else can we see here? Yeah, so there are some problems there. If we look at this column here, for one, we can see this is not going up nicely, is it? You'd think it'd be like, oh, like 500, 600, 700, 800,000. In fact, we see a drop here, and here as well. So there are going to be problems here, which means yeah. So this basic model is not enough. Okay, and this is where you sort of get into the all this stuff in the 20th century coming through, because of course you need quantum mechanics. And I guess the fact it's called quantum number probably means that it's even integrated into that as well. I guess it must be. So yeah. So obviously, well, I don't have a physics series, so I'm not going to be talking about that. But yeah. So this is kind of like Yeah, this is more difficult stuff. So yeah, so a good way to just sort of get into this sort of thing. Uh, yeah, I'll just have to try and invent something here. So say you've got like you know, I'd probably say you've got like a spinning top like this, and then you can imagine like um, if you've got like you've got like uh, like a sort of table here or something. Um, and then there's the reflection of it. So this is like a table, an actual table, not a yeah. And here's a spinning top. This is how you got to kind of look at this stuff, because there's basically yeah. I mean, like I said, it's got to have the word spin. Um, yeah, it's like it's mm, hmm. What's the best way to think of this? I actually did think of yeah. At some point I did actually think about it. It's like yeah. I guess you can imagine like it as like a whole sort of uh, celestial sort of system. So that yeah. So let's get rid of that table and let's pretend that it's kind of like a river instead. Actually, and this is actually instead of yeah. This would be magnetic, wouldn't it? This would be a magnetic thing, and this is more like this is like a river. So this is a reflective thing, and we'll ignore the fact it doesn't actually exist. It's just a reflection, because obviously this is actually a real thing. This is just a reflection, but don't worry about that. It looks a bit more like an umbrella now. Oh, that could be an umbrella as well. I guess it's a river, but yeah. The point is anyway. So there's all these sort of, and around all this, there's like these clouds all around. There's some nice underground clouds too, I guess. I don't know how you get those. Maybe you probably need to have a volcano, magma there, and then of course, yeah, it will turn. I think it will turn into lava once it gets out of the volcano. But anyway, that's not that important either. Um, yeah, so that's kind of like yeah. So these are sort of like charged clouds. And funnily enough, actually, clouds do have some solid particles in them. Actual clouds, I'm speaking about. So yeah, the problem with this topic is it's a difficult topic to look into, but at the same time, it's such an important topic. I've got to really look into it. So I tried to just do a little bit of explanation there. It's a little bit perhaps more esoteric than is kind of accurate, but it's one of those things. And I've also been looking at some biology stuff. A lot of the actual one of the reasons why these courses I'm doing, well, not really a course, but these well, not even I don't know what they are, but any word is unfortunately loaded with meaning. So, but yeah, is that the biology basically disrupted some of this progress. So, yeah, it's just easier to blame biology for everything. So yeah. Anyway, the point is, yeah. So these shell. Okay, so the shell numbers, right? Let's go back to this. Yeah, well, that would be refraction. But anyway, it doesn't matter. Point is, the principal quantum numbers. So, yeah, and we spoke about this, didn't we? So, 2 and 10 and then 18. Okay. Do not have precise values. And you can sort of see, if we're dealing with this sort of like big cloud around the electrons, and they're all spinning and vibrating. You can see that you're getting these exact values are going to be incredibly difficult, even with whatever tools you've got, the what's the TEM, the SEM, the I don't know if you use tomography, maybe that's biology. But anyway, the point is, maybe use it. Anyway, the point is, yeah. So they contain a set of subshells. So yeah, I mean that's an easy way to understand it, I guess. Once we put around the word set, there we go. That's what we like to see. Okay. Which contain orbitals. So it does sound like quite like an astronomical word. And like a lot of things in science, if it sounds a bit like it, it's probably there's a reason for that. But yeah, the orbitals. So it's orbiting around. Yeah. And in a way, yeah. Even though I drew the electron shells like this, like an egg or something. In fact, it probably makes more sense to do them like this. Yeah. Okay, that's another kind of irrelevant point there. But it's kind of worth noting. Some of this stuff is kind of worth noting. It depends. Mileage may vary. Yeah. All right. So, so what does an orbital mean? And let's define it a bit better now. Okay. So an orbital represents a region of space around the atom. So this is the problem when we're thinking about compounds and stuff. How's this even happening? You have to think about heat, thermodynamics, and all this stuff. Yeah, but like I said, this is not a particularly focused episode. And of course, once you're talking about individual, reactions and things like this, it becomes more focused. When you're talking like this, it's you don't want to be generalized. It's not something you want to do. Be generalized. But yeah. Anyway, so the point is, within this region, so everything is kind of probabilistic at this point. There's a high chance you're going to find that electron. But yeah, but if you do want to almost compare it to something with physics, you can imagine the classic sort of double slit thing. And once you observe it, it's different or whatever. But anyway, I mean I don't really like that. There's a high chance you will find that electron. Yeah, so. Yeah, and they're sort of fuzzy vibrating clouds. So yeah. So yeah, so I could start drawing them, and we do. We have to, and like I say, there is this thing with spin. Yeah, and this is the thing. These yeah, I'm not going to talk about this in this episode. I'm going to talk more about it in 11 and of course in 12 as well. But you got to think, yeah, you know, this guy. He wants to get away. Um, and this guy, he wants to get away as well. But unfortunately, they're kind of locked in like this. It's like a locked sort of thing, you know, and it's all kind of you know, in like this sort of it's like yeah, I could say a lot of things what it's like, but yeah, they're locked, and that's the thing. So they spin around, they're paired, they're spin paired. All right, so now there's one more thing actually I want to talk about just before ending this episode, and again I actually spoke about in the last episode as well, and this is to talk about the the block the blocks. I'll refer to the periodic table, but just for now, I just want to mention this, just to actually get some kind of numbers involved here. So the S subshell, 1. And I'm writing caps here. Why not? So yeah, that's the S subshell. P subshell. So yeah, we have to look at the numbers, and we also have to look at direction as well. So yeah, it's kind of like I don't want to say polar coordinates, but I'm kind of leaning towards saying that, just based on kind of, even though I'm not quite sure what's going on here, kind of thinking maybe we're looking at something like polar coordinates here. We will see though. We'll see. So yeah. So it's interesting, isn't it? Because normally you think of them as like they're all going around, they're all around nucleus. It's all nice. It's all like just traveling. It's like motorway traffic. But in fact, well, you think it's just like normal motorway, but in fact it's more like motorway traffic. They're all bunched up like this. But anyway, but yeah, I mean, to be honest, yeah, I mean that's probably a good way to look at it. I'd imagine it seems like a good way to look at it, because obviously you're dealing, you know, you have to deal with this when there's a lot of, you know, all this movement and stuff. It's the only real comparison you can make. All right, so they're the names of the subshells. All odd numbers here as well. So yeah, so I don't really have much else I want to say here. So yeah, I think I'm going to leave it there. I'm going to speak more about this spin thing. It's called something called Pauli exclusion principle. I'm going to talk more about spin and all this stuff, and this will actually carry on for a while. So until that time, thanks for watching.